start with a slide which has a very important message for everyone interested in development. It is a quotation from Aristotle, and you can read what it says. Now, in the last few years, we have been able to show that new and valuable information comes from the study of the distribution of deuterium atoms in alkanes, exchanged over metals, and measured by deuterium NMR spectroscopy. These results are helpful in establishing mechanisms not only of exchange reactions, but of other reactions of hydrocarbons as well. Of course, with deuterium NMR, you can get straightforward information about whether the deuteriums are in primary, secondary, or tertiary positions. But you can get other information about the groupings of deuterium atoms in the products. Next slide. This slide shows results with 2,2-dimethyl-propane, in which one can detect very easily whether the methyl groups contain one deuterium, two deuteriums, or three deuteriums. The point being that if there is a second deuterium in the methyl group, it causes what is known as an alpha isotopic shift, in this case of 20 parts per billion, and if there are two extra deuteriums, in other words, the CD3 group, you get a double shift. Next slide. This slide summarizes the kinds of isotopic shifts. I've already mentioned the alpha shift, which is a deuterium separated by two bonds of the deuteron under observation. And then below that, there's a beta shift, where the shifting deuterium is 3 bonds away. That shift is smaller, it's only about 8 parts per billion. And then finally, at the bottom of the slide, there's a gamma shift, where the isotopic effect is due to a deuterium 4 bonds away, and those gamma shifts is formed. We can always see alpha shifts, we can usually see beta shifts, but we can only see gamma shifts if there are several of them. Now, propane. Next slide. Can you focus it, please? Propane often undergoes multiple exchange, and the most probable mechanism for that multiple exchange is the one shown in the middle, the so-called alpha-beta process, where there is interconversion between alkyl and salt species and alkene and salt species. There may also be a contribution from the lower mechanism labeled alpha beta gamma, which involves allied species as well. Next slide. If we look at some of the groupings of deuterium atoms in exchange proteins that we can detect with deuterium NMR, we find that with platinum, there is good agreement between the experimental distribution determined from NMR analysis and the results from our mass spectrometric data, assuming an alpha-beta process. So, with platinum, an alpha-beta process can explain the results. But with rhodium, as you will see in the two right-hand columns, in every case, there is a discrepancy between the observed amount and the calculated amount, and so it's quite clear that with rhodium, some other process is necessary as well as alpha-beta, and consequently cannot explain the results just on the alpha-beta process. Next slide. Some results now for 2-methyl-propane. And I want you to look particularly at the grouping of primary deuterium atoms which are in color. That is the group and a hydrogen on the central carbon. Now, for the usual type of multiple exchange, it isn't possible to get that species as an initial product. With the alpha-beta exchange, you would always expect to find a deuterium on the central carbon, and so the only time that you will get that species is after you have diluted your deuterium. Now, the results at the lower part of the slide for platinum are okay. They show some of this species, just about the amount that you would expect on isotopic dilution. But rhodium shows far too much. Next slide. This shows further results about the proportion of this species. That's the methyl group with 3 deuteriums but the neighboring hydrogens. And you can see that the results for palladium and platinum follow expectation. The amount of that species follows the dilution of hydrogen as the experiment goes on. But the results of rhodium show twice as much as you would expect. It says 20% of the reaction goes by species other than the alpha-beta process. Next slide, please. This slide illustrates some of the intermediates which are possible to explain these results on rhodium, the alpha-alpha species and the alpha-gamma species, and the one that is not possible, the alpha-beta process. So rhodium is again demonstrating a special facility here for reactions other than alpha-beta. Next slide. These results are for 2,2-dimethyl propane reacting on rhodium at rather high temperature. Now earlier I showed the result with 3 peaks corresponding to 1, 2, or 3 deuteriums in the methyl group. But we now have 2 extra peaks. We have peak C, which corresponds to 2 deuteriums, but with substantial exchange in the remaining 3 methyl groups in molecule. And the combined gamma shifts due to these extra deuteriums leads to a result. And likewise, E corresponds to the CD3 group, but with substantial exchange in the rest of the molecule. So here again, rhodium is showing this capacity for alpha-gamma intermediates and consequent mechanisms depending on alpha-gamma intermediates. Next slide, please. Well, this slide really summarizes the characteristics of the metals which show up in this work. Iridium is particularly good at exchanging primary hydrogens. It's not very good at the alpha-beta alpha exchange, but it does show some alpha-alpha and alpha-gamma exchange at higher temperatures. Palladium is very good at multiple exchange whenever the alpha-beta mechanism can operate, but it's very poor at alpha-alpha or alpha-gamma multiple exchange. Rhodium, as I've said, is the interesting molecule. It seems to form the greatest range of intermediates, and certainly not more than just the alpha-beta exchange. And platinum falls in between. In some ways it resembles rhodium with the branched molecules, and with other less branched molecules it resembles palladium. Thank you.
Thank you, Mr. Campbell, for this contribution. There are 3 submitted questions. The first is Dr. Brigham from Manchester.
Over the last years, Professor Campbell, you've exploited this technique to help us understand the way in which alkanes react on metal surfaces. And the use of NMR is an elegant extension of this. And we see in this paper today the differing reactivities of the group 8 metals. Now, of course, these metals have been extensively studied by surface science techniques for the absorption of a variety of molecules, but alkanes have generally not been amongst them because of their low residence time. Have you got any explanations as to the differing reactivity we observed today in view of these surface science studies on other molecules?
First of all, I take your implied criticism that I have been studying these reactions for rather a long time. I promise I'll give up after another 4 years. Next, to say certain science studies have not been useful in this field. I couldn't agree more. I think certain science studies are often not nearly as useful as some of the enthusiasts suggest. But I'm afraid the answer to your question about why is one metal different from another is, frankly, I don't know, except that it has a different atomic number.
Next question is by Dr. Duras of Montpellier.
Alpha-gamma intermediates were not so popular. I believe mainly because they don't exist on platinum, which has been studied much more thoroughly than rhodium. In the case of rhodium, we propose their existence mainly because we found that when we hydrogenize 2,2,3,3 tetramethyl we get a selectivity of 96% for isopropane. So to cut so selectively the central bond, I think that the simpler idea was to suppose that there was such an intermediate, and I'm very happy that deuterium exchange experiments give a sounder base to that idea. But we found also that that was true on large particles of rhodium. When we go to very small particles of rhodium, around 10 angstrom of size, we get not that reaction, but the splitting of tetramethylbutane to isohexane and methane. So that means that the mechanism changes definitively. And there is an interesting paper by Kogan and Meyer which shows that the mechanism of deuterium exchange and hexane change with the size of the particles. And from their work, they say that if we have well-dispersed samples, we have a mono exchange of hexane, and if we have low dispersion, we have the exchange of two vicinal hydrogens. So if from the results you give in your paper, I believe that I would say that the dispersion of your rhodium catalyst is not very good. And so my question was, have you an idea of the dispersion of your rhodium?
If I may comment first on your earlier remarks, platinum does show a certain amount of alpha-gamma exchange. It is not as efficient as rhodium. Next, when you get to the reactions of isomerization or hydrogenalysis, I think you are dealing with reactions which are perhaps more structure sensitive than those of exchange. Next, I would comment that while the main factor in the behavior of a metal is the fact that it is metal A as opposed to metal B, there are subsidiary factors that matter. One is hydrogen pressure, deuterium pressure. If your deuterium pressure is high, you may obliterate some of your multiple exchange mechanisms, and that is the main reason, I think, why Kogan and Mayer did not see quite so much multiple exchange. I agree with you, dispersion matters, and I think the answer to your question is, I can't quite remember, I'll look it up. Dispersion of 50 or 60% for our rhodium particles of about 2 nanometers in size. Intermediate, in other words.
platinum transaction or butane exchange can also be seen for a cyclopentane exchange of support platinum variety forms, and also for a pentane exchange on platinum flash billet and the platinum 111 single crystal. And the characteristic of the distribution suggests to us that there are two closest. One of the one standardizing multiplex, the observation multiplex. Now the persistence of the platinum number 111 single crystal implies to us that the active site itself is by functional character. So we've developed an image alkane activated by a small concentration site to form a sigma alpha. But this sigma alpha is the weak affinity for by alkene forming, hence it is not the same as sigma alpha can transfer via 1,2 that sigma species onto the secondary site, which is a strong affinity for by alkene, and it is a vicious activation. And for our methane exchange, we have quantitatively almost the results obtained over plastic crystals by black over single crystals in terms of 3 parameters. Now, originally the Anderson-Kendall mechanism was used also to describe the distribution in terms of 3 parameters, but they postulated 2 catalytically independent by both animals contained. Nowadays, with the sigma bond, by bond speaking out routinely observed on the crystals, but systemically unfortunately, we were able to develop because the actual sites are highly important in certain sites. For example, the C5 site of harmful toxins. Even a non-included platinum 111 surface should have density and such effect type catalytic change. And maybe it's possible to actually separate the activity of by functional science. So hence, usually when it comes to characters, algorithms, separate these from today. Okay. That's it. We'll give any comments on that. So the business no answer.
Well, as I understand this comment, it is really an extension of the work and making a possible mechanism for the cited results for platinum, and I really would like to comment on it at this stage.
The next question that will take on.
John Jones, Amsterdam. Professor Kimball, these noble metals can be used for for reduction of nitric oxide by hydrocarbons, say methane and so forth. But rhodium seems to be particularly unique for that. I'm wondering if your exchange reactions and things might shed any light on why this is the case, for reducing nitric oxide with methane to make nitrogen and water.
Well, I just hazard a guess that it may be connected with the capacity of rhodium to form alpha-alpha diasort species pretty regularly with nitric oxide, but it's just a guess.
Dr. Jones, please.
Thank you. Just Campbell, I just would like to ask your opinion on the possibility of other factors playing a role in the distribution of products in society. For the iridium on aluminum catalyst, can you rule out that the alumina is playing a role to give you the methyl exchange, which is the various characteristics of aluminum? And also the possibility that mass transfer effects could be playing a role in rhodium and giving you a different distribution than you would expect in other heat exchange.
To answer your second question first, I think we're reasonably certain that we're not bothered by mass transfer effects. We are heating to relatively low rates of exchange, and we do know that if you let the rate of exchange come too fast, then you are in difficulty. In terms of iridium, I don't think the rate of reaction on the alumina itself is sufficient to show up the results. You can say quite clearly, we are not getting exchange of secondary to deuterium. And getting deuterium to the secondary position, so that the iridium is not doing that. Never mind about what the aluminum is doing, the iridium is not doing it.
Next question by Professor
Professor Kimball, this may have been answered in your paper, but in any case, maybe you can help me. In the case of the exchange of normal butane over platinum, where you have this, what you describe as a U-shaped distribution with substantial T1, substantial T10, and kind of an interesting shear in between. Can you explain in simple physical terms what gives rise to that odd distribution?
No, I would say two mechanisms, or two sites, or if you follow good and negative, two sites but one mechanism.
Preliminary color.
My question has to do with the correlation between, or possibility of correlating the deuterium exchange with the hydrogenolysis activity or selectivity. Follow-up question. It is particle size dependent, but even having said that, that's on most platinum tablets you will tend to cleave from butane the terminal part. Certainly on iridium, you can make two molecules of ether. So if one thinks about where you start dissociating the molecule from your results, you have a secondary to primary ratio with iridium, which is essentially zero. And for platinum, as I recall in the table, it's about 1.5. And so, looking at your results, saying, and guessing at what the selectivity would be, you would have thought terminal carbon cleavage from butane would be what you would expect from iridium, and maybe a mix between terminal and center for platinum, which is just the opposite of C. So my question is, there a chance that the secondary to primary selectivity for deuterium exchange is temperature dependent, because we normally do the hydrogenolysis reactions at 200 to 300 degrees Celsius, and you're reporting these ratios at around room temperature? Or is it just the fact that even though that is the most active hydrogen, and we know now the rate of determining steps of hydrogenolysis is just irrelevant?
An interesting question. Of course, to get a species taking part in exchange, it must be called reversibly. Now, it could be that iridium tends to give central cleavage to butane, because if it absorbs in one of the two essential carbons, it may be more regularly the more highly dissociated species, more strongly held species, which are less reversible and therefore do not contribute to the exchange. There are examples, I don't know that this is the answer to your question, but there are examples where something is formed irreversibly, i.e. an alpha-gamma species on iron is formed irreversibly. Once you've got that form, you've had it. Hydrogenolysis follows, you don't get exchange. So that's what we have to bear in mind. We are dealing in exchange with the reversibly formed species. In hydrogenolysis, we're going on to the ones which are irreversibly absorbed and lead on to another species. No, I don't know the answer. I don't think it's probably very great.
You have 2 minutes left. Please.
I'm wondering about the mobility of hydrogen and deuterium on the surfaces. I've been having trouble myself deciding how fast hydrogen and deuterium move on surfaces. When you exchange a specific position in a molecule, you put hydrogen back onto the surface, and don't we assume that the hydrogen then moves away and gets rapidly diluted, and therefore we can make calculations based on this assumption, but supposing it stays there in the near vicinity and specifically adds state to the tertiary position of your butane, then that might confuse things. So my question is, in this work that you've done, not only over the years but recently, do you have any feeling for how fast hydrogen and deuterium actually move on metal surfaces?
I think if you are exchanging alkanes, you have very rapid replacement of hydrogen by deuterium. After all, to go back a bit, if you take something like hexane, which was done many years ago, the major product from the exchange of hexane is literally over 80% of purging through a molecule. Now that means you have to have a very low chance of retaining any hydrogen that is associated. So when you've got alkanes there, I think you get very good, rapid replacement of hydrogen associated by deuterium gas phase. Once you go to alkenes, it's a different matter.
I'll make a comment on Jared's thing. They move very, very fast across metals and oxides. On oxides, the diffusion coefficients are about 10 to the minus 2 centimeters per second. And they come off of metals at a rate that is blindingly fast.
I'd like to comment on Professor Connor's comment. I'm really wondering if this is true in every case. For example, we have an alkene by the name of apopynene, which isomerizes exceptionally fast. Now, might isomerize without hydrogen, and so then in that case it might be a moot point, but it isomerizes so much faster, maybe 10 times faster than say an ordinary straight chain alkene or cyclohexene, and the exchange seems to be different, and I'm wondering if maybe there is some limit to how fast hydrogen and deuterium migrate, maybe in localized places where perhaps an alkene would be sitting down. And in other molecules which are stereochemically triggered such that when they sit on the surface they flip from, say, a cis to a trans position, you can freeze the deuterium in that position. And I don't think it moves that fast in some cases, but that's a personal opinion.
Yes. Well, I presume the first time